we have seen the molecular orbital theory of hydrogen molecule, we have also seen the valence bond approach, but of the two theories actually even the valence bond theory gives better answers. Simple valence bond theory gives better answers for hydrogen molecule. Molecular orbital theory actually turns out to be easier to use, and it is the one that is most widely used. Even though valence bond theory also is being used by some people, molecular orbital theory is by far the most successful theory, and therefore, we will confine ourselves to the molecular orbital theory, and we will look at some diatomic molecules just to give you a flavor for the way molecular orbital theory works. So, what molecular orbital theory would say is, let me just recapitulate. You have, let us say, two hydrogen atoms. These circles indicate that they have one orbital each, and when you bring the two together, they interact and give you a bonding orbital and an anti-bonding molecular orbital. And this was our HAA, this was HBB. In the case of hydrogen molecule ion and as well as in the case of hydrogen molecule, they both have the same energy, and this is actually the energy of sigma G1s, and that is the energy of sigma U star 1s. And in the case of H2 plus, what happens is that you have just one electron sitting here. Okay, just one electron sitting there, and you can actually calculate the bond energy or energy that is needed to dissociate the molecule. In the case of H2 plus, actually I am giving you experimental values. In the case of H2 plus, you find that the bond length is 1.06 angstroms, and the energy needed to dissociate, or you can call it bond energy. Bond energy in the case of H2 plus is 255 kilojoules per mole. Now, if you add one more electron, you have H2 molecule. That means you have two electrons sitting there, both are going into the bonding orbital, as a result of which you would expect that the bond will get stronger. And if the bond gets stronger, naturally you would also expect that the atoms are brought closer, and that is actually verified from experiment. In the case of this is H2 plus. In the case of H2, the bond length is 0.74. So, you see that it has decreased the bond length, and the bond energy has increased to 431 kilojoules per mole. And as you would know, a chemist will say that there is a single bond between the two hydrogen atoms in the case of H2 molecule. If that is the way it is, you see in this case, how many bonds would you say? The answer is that you see there are two electrons forming the bond in the case of hydrogen molecule. So, in the case of H2 plus, there is only one electron. So, you would expect that it is something like half a bond. And in this connection, it is useful to define something which we will refer to as the bond order. Now, how should it be defined? Well, in the case of it should be defined in such a fashion that in the case of hydrogen molecule, you get a bond order equal to 1, saying that there is one bond, and naturally you would expect that in the case of H2 plus, it should be half. Okay. Now, the definition that I am going to give is a little bit general, because this will cover all the molecules that we are going to discuss. So, therefore, what I am going to say is, okay, number of electrons in bonding MOs, bonding molecular orbitals, minus number of electrons in antibonding molecular orbitals. This is only natural, you see. See, if you add electrons to bonding molecular orbitals, that will stabilize the system, while if you add electrons to antibonding molecular orbitals, it will destabilize the system. So, these cause stability, these cause instability, and so therefore, the net stableness will be obtained if you take the difference between these two, and then of course, you have to say that, okay, if I added 2 electrons to a bonding molecular orbital, that will give me 1 bond. Every 2 electron gives me 1 bond, and therefore, what I will do is, I will take this difference and divide it by 2, and that is the definition of bond order. And if you use that definition for H2 plus, there is 1 electron in a bonding molecular orbital, there are no electrons in antibonding molecular orbital, so you will directly get a bond order of half. The same definition, if you apply it to H2, you are going to get a bond order of unity. Okay. Now, suppose you had a species like He2 plus, right? He2 plus has how many electrons? It has 3 electrons. So, 2 of them will go to this bonding orbital and 1 will go to the antibonding orbital. And therefore, if you calculated the bond order, what will happen? You will get an answer of half. Bond order is going to be half because this will be 2 and that is going to be 1. So, you get a bond order of half. This actually says that He2 plus can exist. It has a bond which is not a full bond. Roughly speaking, bond order is, not roughly speaking, the bond order is half. So, the system you expect is stable and it is possible to make the system in the lab. He2 plus can be made, of course. You have to have sophisticated equipment to make the system. You have to make it in the gaseous phase, but it is possible and it has been made. It has a bond order of half. But now suppose I added 1 more electron, so that I would have He2. So, you would have the second electron sitting here, and what happens? You have 2 electrons in the bonding orbital, you have 2 electrons in the antibonding orbital. Okay, and the way things are, see, the bonding orbital is stable, it is stable by that much amount, correct, because this is the energy of an atomic orbital. So, compared to the atomic orbital, the bonding orbital is stable and the antibonding orbital is unstable by that much. But it is an interesting result of a molecular orbital theory, which we have seen the expressions, and if you analyze those expressions, you can actually find that this height is actually larger than that height. So, therefore, what I am saying is that the antibonding orbital is more unstable than the stability of the bonding orbital, and therefore, if you added 2 electrons here and the 2 electrons there, the system as a whole will be definitely unstable, and the bond order, if you calculate it, will turn out to be equal to 0, right. And therefore, you predict from molecular orbital theory, you predict that the system has to be unstable, and the helium 2 actually there is no covalent bond in the case of He2 plus He2 molecule. Okay. So, now we will look at this definition, we will use later. Now, we are going to look at more complex systems. I will look at systems like Li2, Be2, the first row diatomics. Okay. But before I do that, I want to tell you some general things. Remember, our expression according to molecular orbital theory was HAA minus E, HAB minus ES, HAB minus ES, HBB minus E. You had a square matrix multiplying CA, CB, and you said that this has to be equal to 0. This was our general expression, and then you said that you have to take the determinant of this matrix and put it equal to 0. That actually means HAA minus script E into HBB minus script E minus HAB minus ES the whole square is equal to 0. Fine. Now, this is a simple quadratic equation. Now, remember I am not confining myself to H2 plus or H2. So, I would like to think of maybe the bond between lithium and hydrogen or some such thing. So, therefore, it is not really necessary that the two orbitals A and B are equivalent, and therefore, HAA need not be equal to HBB. Energy of the orbital on A need not be equal to the energy of the orbital on A. That is a situation that I would like to consider. Now, if you want, you can actually solve this equation and find out the values of script E. Whenever two orbitals interact, you can use this equation and find out the energies of the resultant molecular orbitals, because I have two atomic orbitals, they will combine to give me molecular orbitals. But suppose you had a situation where HAB and S both are equal to 0, both of them for some reason, suppose they happen to be equal to 0. Then what will happen? This term will actually be equal to 0, and then you will have this product equal to 0, which means that script E will be equal to HAA, and the other possibility is it is equal to HBB. These are the two roots of my equation. So, what does it tell you? It tells you that if I had a situation where the overlap integral S as well as the integral HAB, which usually is referred to as the resonance integral, that is a term which is usually used. So, if this is called the overlap integral. If it so happens that the overlap integral and the resonance integral are both equal to 0, then what happens? You get the allowed energy levels to be those of the two atomic orbitals, and this actually means that these two atomic orbitals will not combine, they will not mix together. If you try to add them up, you see they refuse to mix together and to give you molecular orbitals. So, if two atomic orbitals are to interact, what should happen is that the overlap integral and the resonance integral both must be non-zero. Okay. Right. So, at least I mean HAB has to be non-zero. If HAB is non-zero, then obviously the orbitals will interact and form molecular orbitals. Now, actually by looking at the roots of this quadratic equation, you can arrive at other interesting conclusions. For example, imagine that this is HAA. This is HAA and that is HBB. So, I am saying that the two orbitals have somewhat different energies. Fine. Then what you will find? You can actually analyze these equations and you can also determine the values of CA and CB, and then you will find that in such a situation what happens is that the new molecular orbitals that result, the molecular orbitals that result, they will have one orbital of energy that much and another orbital of energy that much. Well, this figure has not come out as correctly as I would like it to. So, let me just modify this. Maybe I will rub off this. So, this is HBB and that is HAA. And what happens is that I have a molecular orbital which may be having that much energy, and I have another molecular orbital having an energy of that much. So, what has happened is that these two atomic orbitals have interacted and they have given me molecular orbitals, which I usually draw by representing these lines. These lines simply indicate that these atomic orbitals are contributing to the molecular orbitals. And what is the result that you find? You find that there is a bonding molecular orbital, which I will represent like this, and another antibonding molecular orbital, but the bonding molecular orbital, what you should notice from the figure is that it is closer to the lower energy HAA, while the antibonding is actually closer to the higher energy. Right? This is what you will find, and further you will also find that if you looked at this molecular orbital, it will have its major contribution from the atomic orbital located on A. The major contribution will be coming from atomic orbital located on A, with a small amount of contribution from the atomic orbital on B. And similarly, this antibonding orbital will have major contribution from the atomic orbital on B, with a lesser amount of contribution from A. That is what happens. Okay. And further, as you separate the two energy levels, suppose you separate them and you make them large, then what will happen is that the two orbitals have lesser and lesser interaction. In order to have the best interaction, what should happen is that the energies of the two orbitals should match. If the two orbitals have energies which match, then what will happen is that the splitting or the separation between the bonding and the antibonding molecular orbitals will be large. So, all these conclusions can be arrived from analyzing this simple equation, right. What are the conclusions? If S and HAB are 0, then there is no interaction. And if the orbitals are far apart in energy, if the atomic orbitals are far apart in energy, then the interaction is weak. But if they are having almost the same energy, then the interaction is the strongest, and you will get a strongly bonding molecular orbital as well as a strongly antibonding molecular orbital. So, with this information, let us look at Li2, the molecule Li2. So, in the case of Li2, you have a 1s orbital on one of the lithium atoms, and you have 2s, this is 1s, that is 2s, and you also have 2p on the lithium. On the other lithium also you have the same kind of thing. This is the 1s, you have the 2s, and you also have the 2p. Now, notice the way I have drawn this picture. I have not put a large separation between 2s and 2p. Remember that in the case of hydrogen atom, the separation between 2s and 2p is actually 0, they are degenerate, right. And in the case of more complex atoms, there is the separation due to electron repulsion, right. And in the case of lithium, we still do not have that many electrons, so that the separation between these two is very large. That is why 2s and 2p I have drawn them to be close. Okay. And now what will happen, what I would expect to happen is that this 1s can interact with that 1s. They can interact with each other, but it so happens, I mean, we are interested in the equilibrium geometry of the molecule. At the equilibrium geometry of the molecule, which actually is at a distance of 2.67 angstroms. So, this is one lithium, this is the other lithium. At the equilibrium geometry, the bond length actually is quite large, it is 2.67 angstroms. In comparison with the bond length in H2 plus or H2, see they have bond lengths which are 1 and 0.74. In comparison with them, this bond length is rather large. So, what will happen is that at that large separation, the overlap of the 1s orbital on the first atom with the 1s on the second atom is actually very, very small, they do not interact, and therefore, what will happen, the 1s and the other 1s, you can say, okay, they do not interact at all. So, in the case of Li2, you see these two, you can say they do not combine if you want, right, they remain as they are. So, they are of not much interest. The electron configuration of lithium atom, of course, is 1s2, 2s1. So, what is going to happen is this is going to be occupied with 2 electrons, that also is going to be occupied with 2 electrons, but then you have 2s of this atom interacting with the 2s of that atom, right. So, what will they do? They will combine to give you a bonding orbital, and they will also give you an antibonding orbital. Okay. Let me call this sigma G2s, and let me call this sigma U star 2s. But then you may say immediately that, okay, what will happen is that there are in total there are 6 electrons in the molecule, right. 2 of them are sitting in one of the 1s and the other 2 are sitting in the other 2s. So, therefore, there are 2 electrons left, and what will they do? They will actually go and sit in this bonding molecular orbital, leaving all the other orbitals empty, correct. And actually that is what you can say happens, fine. But then of course, you have other interesting questions. You see, for example, this 2s, can it interact with a 2p on this atom? Let me draw this pictorially. So, you have the first atom, this is the first atom, it has a 2s. Here is the second atom, this is the 2s orbital on the first atom, here is the second atom that has a 2s, and then of course, these two will interact, there is no doubt about that. But now you suppose you think of a situation where I am thinking of a 2p orbital, and the 2p orbital on the second atom is like that. So, this is 2s and this is 2p orbital. 2p orbitals, there are 3 of them. So, therefore, I have to say which orbital I am thinking of, and the tradition as far as diatomic molecules is concerned is to say that the intermolecular axis, the line joining the 2 nuclei, right, that is taken to be the z axis. So, therefore, an orbital which points right in this direction will be called, along the molecular axis will be called an z orbital, and the orbitals which are perpendicular to it, like this orbital which is in the plane of the board, or the next orbital which is perpendicular to the plane of the board, these will be referred to as 2px or 2py. So, this is, let me say, 2px, this one is 2py, and an orbital pointing in this direction will be called 2pz. So, what I am drawing here is actually interaction between the 2s on the first atom and 2px on the second atom. Now, if you think of 2px on the second atom, remember 2px has 2 lobes, one lobe is positive and the other lobe is negative, while 2s is positive everywhere. So, if you think of this object that we refer to as the overlap integral, yes, what would it be? It is going to be, you take the 2s multiplied by 2px, strictly speaking I should put a star, which is actually unnecessary because 2s atomic orbital is real everywhere and 2px also is real everywhere. So, the star is not really necessary, and you take 2s star multiplied by 2px the volume element d2 and integrate over the entire space, what would you expect? Well, in this case what happens is that you are integrating over all regions of space. So, when you multiply these two orbitals together, you see here the wave function for 2px is positive, the wave function for 2s is positive. So, therefore, in this region the product is going to be positive. Now, you have an equivalent region down somewhere here where the product you expect is negative, and these two regions would be the same kind of regions, except that the product has positive sign in one region while the product has negative sign in the other region, and integration, as you know, is a process of summation. So, when you perform the integration, what will happen? There will be regions from which the integral will have a positive contribution. There will also be regions from which the integral will have a negative contribution, and they will exactly cancel each other, as a result of which this overlap integral will become 0. And in exactly the same fashion, if you think of HAB, the HAB would also have these regions where the HAB has positive contributions and regions where HAB has the negative contributions, and they will exactly cancel each other, and therefore, this also will turn out to be equal to 0, and therefore, this is a situation where both the overlap integral and the resonance integral are 0, and if that happens, what is the conclusion? The two orbitals are not going to mix together. So, because of our analysis, we find that the 2s atomic orbital cannot interact with 2px, right. 2s on the first atom cannot interact with 2px on the second atom, and further you can also say that 2s cannot interact with 2py, right. That also is not possible. 2py is, remember, an orbital perpendicular to the plane of the board. But then if you think of 2pz, let me say I have the 2s on one atom and 2pz on the second atom, maybe 2pz will be something like this. See, 2pz is actually pointing towards the 2s. Let me say that I will take this lobe to be positive and that lobe to be negative. 2s is positive everywhere, and then you would realize that, see, when you multiply things out, you will have a significant positive value here, because there the two orbitals actually overlap, right. And if you think of contributions from this region, you see from that region the product actually is negative, because 2px has a negative value, 2s will have a positive value, but the value of 2s in this region, because it is far away from this nucleus, its value is going to be extremely small. So, the contribution from the negative part, by that what I mean is the contribution from regions where the product is negative will be extremely small in comparison with the contribution from regions where the product is positive, and therefore, the net value of the integral will be positive, right. And not only the overlap integral, the same conclusion is valid regarding HAB. So, therefore, in the case of a 2s interacting with 2pz, it is possible to have a definite interaction between the two, right. But then you should also notice that the 2s, here is the 2s and the 2p, that over this 2s and the 2pz there, they do not have the same energy, right, they have different energies. So, suppose that energy separation is large, then this interaction is not very important, while in the case where the energy separation is small, this interaction can be very important. Okay. So, remember that in mind. Then the other thing is, you see, we have seen that this 2px cannot interact with the 2s. So, then which orbital on the other atom can it interact with? Answer is actually simple. You think of 2px on the other atom, its shape would be something like this, right. So, let me draw them in a figure. This is 2px on the first atom having plus and minus, and you can say okay 2px on the second atom would be something like this. And in this case there is a interaction. Why is it that there is interaction? The this lobe and this lobe of this p orbital and that lobe, they are actually both positive. So, if we try to calculate the overlap integral, what will happen? These two will multiply and you will have a region here from which there will be a positive contribution. But similarly, what will happen? You will have a similar region there where again the product, because you see both the functions are negative, so the product is going to be positive. So, the product is actually positive everywhere, as a result of which the overlap integral will be non-zero, right. And therefore, the 2px on the first will definitely interact with the 2px on the second, but the 2px on the first will not interact with the 2py on the second, right. You again, because the overlap integral will turn out to be equal to 0. So, this 2px and the 2py on the second, which is actually oriented like that, they will not interact, and neither will the 2px interact with the 2pz on the other atom. So, with this information, let me think of a general diatomic molecule. Okay, let us think of a general diatomic molecule and ask what are the results. So, you have 2s here. In a general diatomic molecule, you see 2p will not be very close to 2s, maybe it is somewhere here. So, this is 2p and you have 2s, and that is my 2p. When I say 2p, actually you have 3 of them. So, you would have 2px, 2py and 2pz. So, this 2s will interact with the other 2s, right, and you will get a bonding molecular orbital and you will get an anti-bonding molecular orbital. Okay. And that you usually indicate, I will put dotted lines here. And I will call this sigma G2p, sorry, not 2p but 2s, and this is going to be called as sigma u star 2p, sorry, not 2p but 2s. Right. Imagine that this separation is rather large. Okay, the picture does not show that. So, I will move this up. Okay, imagine that this separation is too large. Why did I assume that? Because then what will happen is that this 2s and this 2pz which can interact, that interaction I can forget for the time being, if this separation is large, correct. And then what will happen, the 2p here will interact with the 2p there, I will get a bonding molecular orbital because of that and an anti-bonding molecular orbital because of that. How will you call it? It is going to be called as sigma G 2p, right, and this is going to be called as sigma u star 2p. I should probably draw pictures of these molecular orbitals. How would they look like? So, this is 2p on the first, 2pz and 2pz on the second. Well, I will draw it in such a fashion that I will say its positive lobe is on this side and this is the negative lobe. This is the usual way people would draw it. The first orbital is, I mean, we draw them in such a fashion that they point towards each other. So, then what will happen when if you want to construct the bonding orbital, you will have to just add them up. and if you wanted to construct the antibonding orbital, you have to subtract the second from the first. So, if you added the two up, what is going to happen? You will have a positive lobe situated right in the middle, because you see this plus and plus that plus, they will add up, and I will get this, and you will have a negative lobe on this side as well as a negative lobe on the other side. So, this is actually sigma g 2p. But instead of doing that, I could take this, right, subtract it from the second, which essentially means that I will change the sign. This plus will now become a minus, and that will become a plus. After changing the sign, I can just add them up. So, if I did that, what will I get? I will get some orbital which looks like this. This is going to be minus, here it is going to be plus, then you will have a plus minus here, and then you will have a plus here. Correct? Now, if you look at this, you can ask how many nodes does it have, the way it is drawn. Well, you see this will have a node somewhere here, because when separating the positive and the negative region, there should be a surface, and it will have another node there. This is a node, they both are nodal surfaces. So, this has two nodes. What about this one? There will be one nodal surface somewhere like that, there will be a nodal plane like this, and then there will be another node like that. So, therefore, this has three nodes, and that essentially is the reason why this is not bonding, while this one actually is bonding. Of course, you could also say that if you put electrons into this orbital, the electron density goes into the internuclear region, while if you put electrons into that orbital, electron density does not go into the internuclear region, and therefore, this is bonding while that is anti-bonding. So, this one we will call it sigma u star 2p. And what does sigma mean? It is just the same as I have told you earlier. These are orbitals that have cylindrical symmetry about the z axis, about the internuclear axis. You can see that if you rotate it, this orbital about the intermolecular axis, the orbital remains unchanged, the appearance of the orbital remains unchanged, and that happens with this also. So, these are sigma g 2p and sigma u star 2p. So, those I have represented. Okay, and the orbitals actually, these 2p orbitals, what do? They will interact, and they are pointed towards each other, and therefore, you would expect that the overlap and consequently the interaction is rather high. Now, suppose you think of 2px here and 2px on the other side, right. We have already accounted for the interaction of 2pz on this side with 2pz on the other side. That we have accounted for, because that is how this bonding and that antibonding orbitals are formed. But now, suppose you think of 2px on the first. Again, let me draw a pictorial representation of 2px. So, here is 2px on the first, and there is 2px on the second. Clearly, the overlap integral is non-zero, but unlike the overlap between two pz's, two pz's were pointing towards each other, but these are not pointing towards each other, they are just overlapping sideways, and sideways overlap is not as efficient as overlap in the case where the two orbitals point towards each other, and therefore, you would expect that the value of the overlap integral as well as the value of HAB, you would expect that it will be lower. So, therefore, these orbitals interact not as strongly as the 2pz, and therefore, what will happen when they combine to form bonds, right, when they combine to form bonding orbitals, not bonds. When they combine to form bonding orbitals, what will happen? The splitting of these orbitals will not be as high as in the case of 2pz, because the value of HAB as well as the value of S is smaller. Okay. And further, so therefore, if you think of 2px interacting with 2px, can 2px interact with 2pz on the other? No, definitely they cannot. overlap integral is 0, it cannot interact with 2py on the other. Again the overlap integral and the resonance integral are both 0. So, therefore, 2px on this can interact with only 2px on the other one. And what will you get? You will get a bonding orbital, okay, and you will get an anti-bonding orbital. And as I have told you, this splitting is larger because the overlap is larger, while this splitting is smaller in comparison. Okay, and what will happen if you just added the two orbitals together? If you just added these two orbitals together, you are going to get the bonding orbital. How would it look like? You would have a positive region here, the wave function would be positive there, and you would have a negative region down here, simply by adding that you can see. Okay. So, here are the two nuclei. The other possibility is actually to subtract the second from the first. That means you are actually multiplying this with -1. So, this lobe will become negative and that lobe will become positive, and then you add. So, what will happen? You will have a negative lobe here, sorry, you will have a positive lobe there, then you will have a negative lobe here, a negative lobe here, and a positive lobe here. Correct? That is how it is. I mean, all that you need to do is multiply the second orbital with -1 and then simply add. That is what is going to happen. And you would realize that this has one node. Where is that node? Is the 2px has, both the 2px's have nodes. Where are they? They are in the yz plane. Right. So, therefore, when you add the two up, you are going to get that node. So, therefore, there is a nodal surface. It is actually a plane which is actually the yz plane. So, this has one node. What about this one? Well, the yz plane is a node for that, but in addition to that, you have another node which is one more plane like that. So, the energy of this is larger, while the energy of this is lower. It is bonding, and that is actually anti-bonding. Now, these orbitals that I have described, sigma g 2s, sigma u 2s, sigma g 2p, and the other one, they were all having cylindrical symmetry about the z axis, about the internuclear axis. But this one, if you look at this, suppose I rotated this orbital about the z axis, this is my z axis. If you rotated the orbital about z axis by a small angle, you see the appearance will actually change. If you rotated it by 180 degrees, what will happen? This positive lobe will come here, the negative lobe will go there, right. So, therefore, that would be actually equivalent to multiplying the orbital by -1, right. And then if you rotate by 360 degrees, of course, the orbital's appearance is unchanged. So, orbitals which have this kind of symmetry, they are referred to as pi type molecular orbitals, right. So, therefore, this orbital is actually a pi type molecular orbital. Okay. It has come from 2px, its origin is from 2px, right. And further, suppose you perform the operation of inversion. If you inverted this orbital, remember inversion, how do you do this? You invert it about the center of the molecule. If you perform the operation of inversion, it is obvious that the orbital will change sign, and therefore, this has to be classified as ungerade. And therefore, I will say that this is pi u 2px. On the other hand, if you are thinking of the anti-bonding orbital, which is shown here, this is actually pi u 2px. If you think of this ungerade orbital, sorry, if you think of this orbital, it is pi, because if I rotate it by 180 degrees about this axis, about the molecular axis, the orbital actually changes sign. So, it is pi, and if you rotate by only a small angle, it actually the appearance itself will change. So, this is actually to be classified as pi, but if you look at this, it is actually having an inversion symmetry, because if you inverted the orbital about the center of inversion of this molecule, you will find that the appearance is unchanged. So, therefore, you will say it is pi g, and it has arisen from 2px, and in fact, it is anti-bonding. So, therefore, if you like, you can put a star there to indicate that it is anti-bonding, right. So, these orbitals, the one is pi u 2px and the other one should be called pi g star 2px. Now, further whatever I have told you regarding 2px is actually valid for 2py. 2px and 2py are not very different, they are different only in the sense that their orientations in space are different. Okay. If you say 2px is in the plane of the board, 2py is actually perpendicular to the plane of the board. So, there is a 2py here, there is a 2py there, they are going to interact just the way this 2px interacts. Right. So, what will you get? You will get a bonding orbital and an antibonding orbital. Their appearances are going to be exactly the same, except that they will be in a plane perpendicular to the plane of the board, like that. So, therefore, and further they will have precisely the same energy as these orbitals. So, therefore, from the combining together of 2py here with the 2py there, you will get one more orbital having precisely the same energy as this. This is actually my pi u 2py, and here again you will get one more orbital, right, and that will be pi g star 2py, right. So, this is what happens if the energy separation between 2s and 2p is large, and this will be the order of the energies of the molecular orbitals. Sigma g 2s will be the lowest, and starting from there it goes on increasing, right. This is the way if this energy separation is large. This energy separation is large in atoms which have sufficiently large number of electrons. So, for example, if you think of oxygen atom or fluorine atom, this is actually fine, this picture that I have drawn, because this separation is large. But if you thought of something like a carbon, or if you think of B2, right, this energy separation is not large, right, and if that energy separation is not large, obviously what will happen is you will have to draw closer, but then what will happen is that you see this 2p z here will interact with the 2s there, the interaction is not small, and similarly the 2p z there will interact with the 2s here, as a result of which what will happen, the result is that you see when they have interactions, the energy of this orbital will get lower, the energy of this will go up as a result of this interaction because of this contribution. So, therefore, what happens is that this energy level goes higher, and these energy levels, actually what will happen in any interactions, whatever is higher will go further higher, and whatever is lower will go further lower down. So, you can say, okay, these two orbitals actually in a sense they get pushed down, while the two higher lying orbitals, this one and that one, these are the orbitals that involve 2pz. So, they will get pushed up, right, and therefore, for a molecule like carbon or B2, the orbital order is little bit different. So, the orbital order is actually going to be, quickly let me try to draw this. I hope, because I have been quick, I have to be careful in checking. This is actually 2s, that is 2p, this is again 2s, that is 2p, this will be sigma g 2s, this will be sigma u star 2s, this is what happens is that you see these two orbitals, their order gets interchanged. So, this will get lower. So, therefore, this is actually going to be phi u 2p. I will not put the subscripts x or y, it could be x or y, they are both having the same energy. Then I would have the next one, this goes above. So, I would have sigma g 2p. What is the next one? The next one is actually pi g star 2p, and the last one is sigma u star 2p. So, this will be the order in which the orbitals are in the case of diatomics like B2 or C2. Okay. So, we will use this in the next lecture. So, you have to draw the these lines. I will draw them clearly in the next lecture. Thank you for listening.